Except I would just feel bad since I kind of already promised somebody. Yeah.
So you mind working on the number 2, the 3.9 that we didn't get to?
What's that? What's the
3.9, the related rates? We never got to the second.
Oh, yeah, sure. Where did I put the extra? Shoot. Here we go. So there's a handout. Anybody need that handout? The related rates handout from last time? Anybody need that?
Was it section 3.9?
3.9, yeah.
I think the last one.
Conical tank one. Alright, that's another thing we can talk about. Let's see. So where to start? Let's start with this. I kind of like to work backwards when I can in a review. I'll work up here on the board. I'll turn this dude on. I think we finished the first part of it, right?
Yeah.
Yes.
The second part with the street lamp that was defying all kinds of laws of physics, just hanging there in the sky. 6 foot tall woman walking at the rate of 4 feet per second for a street lamp. So I got this woman. There she is. She's horribly underweight. Walking at 24 feet off the ground. There's this lamp hanging there. Okay, so what? So she's 6 foot tall. This is 24 feet up in the air. Any idea what to use here? Where's her shadow? Yeah, her shadow is this way. So it kind of naturally breaks itself up the way we need to. So let's say this is her shadow, right? The closer she gets to that light, what's going to happen to her shadow? It's going to get small. Yeah, the further you get away from it, it's sort of like putting a flashlight on somebody and then just taking you down, their shadow just grows out forever. And you're going to see why geometrically here, because what shape, if I finish out one side, I get a nice, I get a nice triangle. So you can see, that shadow has actually got to fill in that triangle. It's kind of neat. So as they walk towards it, it would kind of, she would come here, it would be like that, the shadow would be much smaller. Cool. Okay. It's really kind of cool. Something you don't really think about what controls those shadow links. So there's a couple things that I kind of in the questions I kind of give you a hint as to how you could set this up, and this is not the only way to set it up. But it's got to be something like this. There's 2 unknowns here really, in general, and not rates, because the rates are a separate thing. We want to talk about just the setup here. What are the 2 unknowns I still haven't identified? And you might think there's one, but there's a piece of it.
The horizontal distance.
Yeah, this whole thing.
Two parts.
And also just the shadow, right? So if we call her shadow X, and we call this part Y, because we're creative people, then the whole thing would be X plus Y, so forth. Right? Is that cool? Okay, so now we've got our situation completely set up. What rules the day here with relationships between the various?
Similar triangles.
Yeah. So what can I set up similar triangle-wise?
24 over Y, or X plus Y.
Careful, yeah. Yeah, be real careful. So the big side length over the big side length, 24 over X plus Y,
Equals 6 over X.
6 over X. The small triangle side length divided by the small triangle side length in the same ratio. How are we doing so far? Is that cool? So in one sense, it feels very much like a geometry problem, a pre-calc problem maybe even, just setting up these ratios. But it's different because, of course, now we're talking about rates. What rates do we know?
You have your dy dt.
Yeah, we know how quickly she's moving towards the lamppost, which is the dy dt. I love it. All right, so be careful. It didn't say anything about dx dt. That's how quickly her shadow is changing. So she's walking. That's directly affecting this y. So I know that dy dt is 4 feet. And it's actually negative, but we'll deal with it. No, I'll make it negative. And it's negative because it's shrinking. That's the only reason. Because she's getting closer to it. So, of course, y is getting small. Okay. And then the question asks, the part A says, how fast is the length of her shadow changing? So that's this. So what, for part A, what's the question in symbols?
You find dx dt.
Yeah, in symbols, I want to know the rate of change of x. So that's dx dt. So I really, there's no way I can control how much you understand what I'm saying here, but you desperately want to write in symbols what they tell you, and you desperately want to write in symbols what they ask you, because then that keeps you on track for what should be showing up when you do your calculus, right? So if you don't have a dx dt showing up, obviously something's not good, right? Yes, sir?
Do you have any more of the related rate?
Oh, yeah. Oh, cool. I have the one that I did the work on. So what do we get from this work here?
4x equals 6x plus 12.
Okay, so then I get, this is cool, I get 4x equals x plus y. So then
dx by dt.
3x equals y. Yeah, it's not a bad idea to simplify first, any situation you have. So that's the immediate thing we can set up. Please, dear God, if you start doing derivatives, it'll work, but you're forcing really ugly things to happen. So simplify, simplify, simplify. I can't really simplify any further. I can just move stuff around. So now I can attack it with calculus. And if I attack this, let me stop right there because I'm moving a little fast. But is everybody semi with me here? This idea of related rates, so the whole shadow thing is this is so much a related rate thing. You see, this is it's even less than that. It's a similar triangle thing, really, right? What do we get here when you do calculus on this?
3 dx dt
Good.
equals dy dt.
Coolness. And I know that dy dt is negative 4, so that's pretty damn simple now, right? So dx dt must be
Negative 4 with
so negative 4/3. What's a what?
Feet per second.
I get feet per second. Cool?
Yeah.
Cool. Okay. Now, just once she's right underneath it, or if she bangs into the pole, if there is a pole, or she's right underneath it, if there's some magical force hanging it up in the air, her shadow length and this away will both be 0, because now she's right underneath it. The shadow is basically not there, right? Because there's nothing to cast on; it's on herself. So, and then if she goes forward, we're still calling this the negative direction. This is all on the side, by the way. This is all. But she could continue walking past, and all of this would still hold true. Because it would just, now it would be growing in that direction. It's still negative, but I'm calling that the negative direction. So it doesn't matter that she's on this side. It just matters which way we call negative. I don't know if you guys understood what I just said, but it doesn't really change anything. Negative 4/3. Part B says, how quickly is the tip of the shadow moving? So that's different from the length of the shadow. How quickly is that moving? Would really be a question of how quickly what distance is changing.
xy.
X plus y. I like it. So how quickly is x plus y changing? That's a neat question. So now I want to know x plus y. I want to know what this how quickly is that changing?
Where do you get the d of x plus y?
Well, that's just from the question, right? How quickly is this length changing?
Okay.
Yeah. So, what do you think? Well, how can I approach that?
We can assume x plus y equals to z, so we can z over 24 is x over 6. And we have one.
Yeah, we've already got this relationship here, right? There's a couple different ways to do this. So I just wanted to wait and see which way you guys wanted to approach it. So, I know this is true. So then I know that if I just kind of work with this a little bit, x plus y equals what?
24x over 6.
Yeah, so 4x, right? And we already knew that x plus y equals 4x from right there. Is that cool? So x plus y is 4x. And then you're going to attack this with calculus. And when you do this, you want to do d dt that. Does that make sense? Because that's what I want to know. I want to know how quickly is this length changing. So that's a little weird. And that'll equal d by dt this. And that's the easy part. 4 dx dt. And dx dt is what? Yeah. So it'll be just 4 times that. Yep. All right, so you get negative 16 thirds feet per second. Yeah, I'll get the same thing the other way. There's another way to do it that's a little bit more direct. What is this equal to? Just in symbols, just theoretically. What's the derivative of a sum?
Dx plus dt.
Yes, dx dt plus, what's dy dt?
4.
And what's dx dt? So it should be negative 4 thirds minus 4, which is negative 16 thirds. Right? That's a little bit quicker way to do it. Thankfully, both ways come out the same answer. Who cares? But it's all this is the part you guys got to get used to. There are some categorizable problems in here. There's some shapes that show up all the damn time. I personally like stuff that falls and makes a cone or something. Cones always show up, where you have the trench filling with water, where it's a trapezoidal end. Oh yeah, that would be fun.
That trough.
Yeah. Blah, blah, blah. You with me? I mean, but they always have the same kind of feel to them. These kind of problems, you normally are given some relationship. There's similar triangles, or there's some kind of something you can set up to get a relationship between the variables. So you don't have so many variables around. You get a function of just one variable. And you make sure the variable that ends up staying is the one they actually ask about. You with me? Right? You don't want to get rid of the wrong dude. This one is almost, believe it or not, it's weird to set this up, I think, sometimes. And it's weird to get an idea of what this question, like part B, really is asking for. But the math work in this is stupid simple. The hard part about this is setting it up. Now, in a lot of these problems, it's the opposite. The actual setting it up part is not too bad, but it's the math part that gets kind of weird. So I don't know. Okay. So that's that handout. I had one other problem I definitely wanted to do. I think I'll do that, and then I'll open it up to whatever you guys want to look at. I promised somebody that I would look at section 3.7, number 1. Because you know I'm going to give you a problem. Something like this. But you've already seen on the practice test the twist I put on it. I still love how fast the train is going a half hour before it gets back. That kind of thing is not difficult when you see how to do it, but it's just a question of really stopping yourself and seeing how to do it. It's also a question of plugging this stuff back into the right function. Right? You have a position function, a velocity function, acceleration function. You plug it in the wrong thing, you get it 0 because you just set the damn thing equal to 0. You probably want to plug it into the position function to see where it is when it's turning around or something. So this one starts off, it looks kind of nice because it's a nice polynomial, right? The position function they give us. I'm going to call it S.
3.7.
Yeah, this is 3.7. Sorry, thank you. So of course, before we even do any of the questions, what's the velocity function?
3t squared minus 4t.
And acceleration.
16 minus 24.
Okay, cool. Right. Nice. Is the velocity is just S prime, acceleration is just double prime. Right? No questions about jerks. So we don't have to worry about triple prime. So part A says find the velocity at time t. Okay, that's part A. Check. B, what's the velocity after 3 seconds? Okay, I don't have to do that. Check. All right, plug a 3 in there. Okay. C, when is the particle at rest? For some reason,
S60.
I always get somebody. Yes, sir.
Just to go be real quick, that'd be plugged into double prime, right?
Yeah, exactly. I'm glad you said So the one thing to be careful in part B is to say, how fast is it moving? Or what's the velocity after 3 seconds? So you want to plug it into the velocity function. So call this V. Say S prime V. So then when they say velocity at 3 seconds, you know exactly which one to use. There's no question, right? Because it does get a little weird, especially when we start graphing these things and we just have a function F. And then you have F prime and F double prime. They all mean different things. You got to know exactly which time. V of 3 is whatever it is. C. When is the particle at rest? Set the velocity equal to 0. That does not mean plug a 0 in. What would that be? If I plug a 0 in, I get the velocity at time 0. I want to know at what time is the velocity 0. So if I set the velocity equal to 0, I can factor this thing, take a 3 out, and then this factors to be
6 by 2.
yeah, minus 6 minus 2, so at t equal to 2 in 6 seconds. Considering these are both multiplicity 1, oh yeah, what's happening at those times exactly? What do those have to do with each other? These are multiplicity 1. They're both to a first power. Odd multiplicity is what's important here. What is truly happening at that time then?
Changing direction.
Change direction, because the velocity is 0 at those positions. It's going to go through at zeros because its multiplicity is odd, so it's actually going to change from positive to negative, from negative to positive, right, guys? Kind of with pre-calc is going to be seeping in here pretty hard, right? That's why they call it pre-calc. All right, so I know this for part C. I'll be out here in just a second. That's when the particle's at rest. When is the particle moving in the positive direction? So now they're just really hammering home what's going on. Now, there's a lot of ways to do this. This should look fairly familiar from pre-calculus, but now we're going to be looking at this function. So it is calculus, it's a derivative, but who cares? I know it's 0 here, I know it's 0 there. And if I plug a 0 in, what do I get? No, I just factor the 3 out. I'm not going to change this. So I get negative times negative, I get positive. What happens when I plug, and of course they're all multiplicity, odd multiplicity. There's a lot of shortcuts here, but embrace the shortcuts. If I plug a 4 in, I'll get negative times positive. I already knew it was going to be negative. It's going to change signs around at 0. That's the multiplicity odd. Multiplicity even, it's going to turn. It's going to stay the same sign. I'm hoping that sounds familiar to some of you guys. Pre-calc a long time ago for some of us. Or that part didn't make any sense. I don't know. And then what about up here? It's got to be positive. It's got to change because, again, it's odd multiplicity. But you can investigate each one. Just plug a number in, see what the sign is. So where's the velocity positive? When is it moving in the positive direction? I think they gave us, t greater equal to 0. You put 0 on there. So when is the velocity positive?
0 and 2.
Yeah, from 0 to 2. 6, we're going to assume it's, or we'll do is just going to keep on moving the rest of its existence. They do eventually give it an 8 stopping point, but poor little dude. How are we doing so far? Is that? Yes, sir.
How would we make like that examples graph where it goes left and right?
Yeah, we're about to do it.
Okay.
And I want to point out, this is the long way to do it. For this particular one, this is a quadratic. It's a parabola that opens up. Therefore, it only goes negative in between its intercepts, right? It's opening up. It only goes negative in between its intercepts. Then we get that answer a lot quicker than going through this. Cool. E. And F, I would do F before E. I have no idea why. F before E, except because so you start at 0 seconds. Now here's the thing. This is not time. This is position. So it's 0 seconds, and we don't draw back on top of itself just so we can see better what the hell's going on. So it's 0 seconds, and then I'm moving forward. I know I'm moving forward, and then I turn around at 2 seconds, and then I turn around at 6 seconds, and I turn around at that's it. So I'm going to come back and find that picture later, because like we saw last time, what's important is when do you actually stop, or do you make it back to where you started? Yes, sir.
So you're going forward 2 seconds and you're going back by 6. So you'd be like,
Well, you go forward for 2 seconds, then you go back for the next 4 seconds, because it's 6 seconds later you turn.
okay,
You get it?
yeah.
It's not an absolute, like, in between each. It's an
You
absolute.
want to end up back at 0.
You don't want to do anything. It's what is it doing? You can't control what it's doing. It's doing this. We're investigating what it does then. Right? So because the function is this, it turns at 2 in 6 seconds. So in part E, find the total distance traveled. So this is like F and then E. I can refine this a little bit. Now I know my turning points are 2 and 6. So what am I really curious about when asking for total distance at those times? If I want to know what the total distance is, it's gone. At that time, I want to know... Yeah, because where does it start? What position does it start at? Starts at 0 position. Well, where the hell is it at 2 seconds? And then where the hell is it at 6 seconds? Right? If I just know those, I can figure out the total distance I've gone. And it says between, during the first 8 seconds. So then I want to know 8 seconds, where the hell is it? Right? So there are 3 things I want to figure out here. I want to know what S of 2 is. Where the hell is it at 2 seconds? Where the hell is it at 6 seconds? Where the hell is it at 6 seconds? So you guys have to help me out there. What's S of 2? 32. S of 6? 0? Yeah, because it's factors. And S of 8, I think, is 32 again. That's easy enough, right? Let's just plug in points in. Now let's make it make sense on the picture here. So it goes 32, then another 32, because it's 6. Where is it?
0.
So it went back to where it started at 6. So it's right there at 6. So it's 32
32.
plus 32.
So 2.
And then it stops 8 seconds later. It's right there. 32 plus 32 plus 32. Right? No absolute value shift required. You could if you want to, if it makes sense. To me, that stuff didn't make any sense. It's just easier to draw something like this and just get the appropriate distances that you need. This 32, where did it come from?
The distance from 32 back to 0.
Yeah, 32 back to 0. And if I would have went past it, I would have still done 32 and 32, and then I would have just, whatever, if 6 would have been negative 10, it would have been 10 more feet back. And then I would have added the 10 back on to get back to 0. I mean, it's the problem itself is not mathematically intensive. It's how to represent it to yourself so it makes sense. So all you guys didn't know what the book was trying to do, and there's other ways to do this if you could figure out your own way, but that way works. All I can think of right now is Superman. S of one word. Yes, sir.
I figured that was like that.
So you plug in S of 2. Okay, no, see.
So if I know when my turning points occur, it kind of makes sense. I eventually want to know how far did I make it before I turned, especially when they start to ask me about total distance I've gone. So when my turning points occur, where the hell was I at those turning points? Together, that will tell me how much total distance I've gone. Maybe.
So on the test, you're going to ask the turning points first and then the distance?
Yeah, I normally ask it in the order. I always hated my physics class. I always did part B and then part A. I'm like, is there a way to do it the other way? And sometimes my professor would say, no, I don't know why they answer like shit. So here, I don't know what you have to do F to really help you answer E. You have to draw this out. G is acceleration. Just plug a 3 in.
In 4 seconds.
So where are we at?
No, question here. From 2 to 6, 4 seconds.
Yes.
The same distance like from 0 to 2 seconds?
Yeah, so what was happening in between here? It was going... Well, it took longer to go the same distance, so it's going faster here. And you're like, yeah! It's like, oh... Right, when it's slower back. You with me? Yeah, so that definitely do that, right? This is not symmetric. It's not parabolic around its turning points. You with me? Right? It can definitely have like that and then like, wow. Yeah. Okay, is that cool? Yeah, it doesn't have to be symmetric. It's not a parabola, so there's no need for symmetry around its turning points. Is that cool? That's actually a really good way to look at that. The rest of it should be simple enough, right? How do you see when it's speeding up and when it's slowing down?
Just look at it.
Slope.
Acceleration.
Yes, acceleration. All right, you gotta look at the acceleration. Just like the velocity tells you when is it going forward, when is it going backward. Acceleration and
Tells you at that point when it's.
tells you the points where it's speeding up, slowing down. Yes.
When we're actually trying to show the graph, do we honestly have to show it? Can we just skip that part?
Yeah, what's it say? Graph those. Yeah, you just graph it. That's fine. You can kind of draw a rough sketch for me.
I know.
It's never a bad idea. Yeah. Okay. All right. So now it's wide open. Whatever you guys want to focus on.
We'll do a 66 on the practice test.
Number 5, number 66.
Yeah, it didn't seem that hard looking at it, but for some reason, I don't know. I think I was doing something wrong. Just
Oh,
more
yeah.
simple.
It's got a little weirdness to it. So number 5 references the book on page 265.
I can give you the wrong if you want.
I got it. So it talks about this ellipse here. They want to find out where the tangent line has slope 1. Find the points where the tangent line, and if you just draw, what kind of an ellipse would this be? Does anybody, would it be longer in the x direction or longer in the y direction?
There's all stretched out in the line.
So it's really like this, right? So it'd be 1 in the x direction, and square root of 1/2 in the y direction.
I guess.
You guys with me? Yeah, so you gotta be careful when it's actually the inverse of what it looks like. So it would be a little bit longer than it is tall. And I wonder why the slope is 1. So it looks like the slope would be 1 like here and there. Does that look, do you see what I'm saying?
Yeah.
Now, of course, here it would be
Negative.
-1. So so it looks like I should get 2 answers. I mean, there's nothing in the problem says you have to do that. But I would graph the damn thing, right? In the calculator, you can solve for y and plot the upper and the lower if you want to, and then it always looks freaky as hell. But just plot an ellipse real quick and see what makes sense. So I should get a point like positive, negative, and negative, positive. Right? So I know all that much just by looking at the picture and seeing what makes sense. Of course, what do I have to do to this to really find out where the slope is doing something?
Differentiated.
And what kind of differentiation do I have to use? Because I could solve for y, but I couldn't really because it would take 2 functions to do it. So I can solve it implicitly. So here,
2x
2x.
plus 4.
Or when it was here.
I like it.
Go 0.
0. Cool. The worst thing is when somebody forgets to differentiate that side, there's like a whole lot of stuff to do after that. It just really sucks. So if I do this, dy dx, subtract, divide, cancel.
Negative.
So what,
X over 2.
what am I doing? Thank you. Negative x over 2y. And then you want what to happen with that?
Equals to 1.
Yeah, you want to make that equal 1. Which then tells you that x equals
Negative 2.
-2y. Is that cool? So I know that x must be -2y in order for this to work. So 2 things have to be true about x and y. This must be true, and they have to be a point on the ellipse. So what can I do with this? If I have 2 things that are true, I can use substitution. I can just use linear systems. And it's not linear, but it's systems of equations. So plug -2y in for x. You guys kind of with me? Because you might get to that point and be like, okay, I was hoping for some number or something. But you get a relationship between x and y, you have another relationship between x and y, use them both. So if you plug in -2y here, I get
4y squared.
so you get 6y squared is 1, so y equals,
1/6.
what about 1/6? What about square root?
Plus or minus.
Yes, sorry. When I take a square root, you got to do plus or minus. That's still not a point. That's the parts of 2 points. So the question is, at what points does this have a slope of 1? How do I find x? It's almost too easy.
Like right here.
I know that x is negative twice y. So this is what I would do. So for positive square root of 1/6, it'd be negative 2 times that. For negative square root of 1/6, yeah. So there's another, you don't have to write it like this, by the way, but I just want to. That's an example of where minus plus is different from plus minus. So what are the 2 points we're really talking about then? There's negative 2 square root of 1/6 and positive square root of 1/6. That's this one. And then, of course, positive 2/1/6, negative square root of 1/6. That's that one. You can write them separate like that, no problem. Okay? So it's calculus. It's the first real place you have a ton of stuff behind you. You learn new math that then builds on the old math. Right? Systems of equations, substitution, that kind of thing comes into play. Okay?
About 101? What is that sign?
Good, because that's one I didn't put on the answer key, actually. Blah, blah, blah. Okay. So 101, let me let you guys read through that. This is page 267.
I'm using my PDF.
So let me help you out with a picture of it, because pictures will. So I'm interested in the shadow of this building. So, all right, the woman that was walking earlier, she's in the building. Here's the sun. So the shadow is going to be. Oh crap, Joe. Shadow of the building is going to be there, right? Okay, so that's the situation we're in. Where's the angle that they talk about? Angle of elevation to the sun.
What is that, Tom?
Yeah, so angle of elevation depression is always in relation to the straight horizontal. So angle of elevation is how far I've got to look up, the angle I've got to pass through to look up to it. Or if I'm in a plane angle, descent, the angle of, what the hell's the word? I just forgot. Depression. The depressing angle. Okay. Here's the angle I'm talking about. That's the angle of elevation. And they say it's decreasing at a rate. So what's that? How do I use symbols? What they say? Decreasing at a rate of 0.25 radians per hour.
D theta.
Good. D theta, dt is negative 2.5 rad per hour.
The height on the building as well. We got 400 feet with it.
Yeah, and we got 400 feet on the building. And they're asking how fast the shadow cast. So what do you think I should call this?
X.
That's crazy. All right. So now again, it feels like a pre-calc problem, but they've just thrown questions about rate. So in pre-calc, it would have been a question of, the angle's 35, so how far away am I? You know, that kind of question. But now it's, how quickly are things changing? So it's the same setup, we're just doing more to it. What's the relationship here?
Tangent.
Yeah.
All right, so how that works? Tangent theta?
400 over x.
Yeah, 400 over x.
This is Gala.
And then I would do at least one thing to this to make it a little bit easier to look at, to work with. You could make this 400x to the negative 1 and do all that crap. Or you could multiply the x up. We're going to have to implicitly differentiate this anyway. Yeah, exactly. You can make this x tangent theta is 400. I use cotangent, but it doesn't matter. I use cotangent just because it makes the x go on top. Right? But it doesn't matter. If I take the derivative of this, what do I have to do?
By parts. X.
And let me just show you.
Oh, again, the channel.
This is what? This product. Good. Because they're both functions of
T.
t. the shadow's changing as time changes, and the angle's changing, and that's why the shadow's changing. They're both changing because. Another way to write this is x equals 400 times cotangent, which would take the product rule away. Do you see what I'm saying? So it's if you don't see how to rewrite something to make it simpler, it's okay. You can just attack it the way it is. But if you think about it for a second, is there a way I can write it so I don't have to do that? It feels like cheating almost. Like, I don't like product rule, so let me write it like this. Now I don't have to do product rule. Well, it's awesome because it's true. If it's true, then you can do it. Right. So I don't know which way. I'd rather not do that. What's the derivatives over here?
400 secant squared, or
dx by dt.
dx dt?
or cosecant, I think it is. Or cosecant squared.
Almost.
Negative.
I didn't hear it. I don't know if I heard it. Negative 400?
Cosecant.
Cosecant.
D
d
theta.
theta by dt.
d theta dt I love. All right, cool. Is that cool? Because anytime I take a derivative with respect to something that's a function of time, I've got to do that chain rule, right? That theta is a function of time.
Oh yeah, and the sun's at pi over 6.
Good. And I know the angle, thankfully. They had to tell me the angle because I have a straight up dependence on theta. I have a dependence on the rate of change of theta. And that's what I know here. But they sometimes tell me at a time when... And they sometimes spell... When the angle... Good Lord, Jeff, how tired are you? Angle is pi over 6. Just got to plug and check. It's nothing major. All right, pi over 6 is a nice thing. And to tell you honestly, if you screw it, sorry, you can just work with it the way it is. Negative 400. What's cosecant of pi over 6?
2, I think.
Maybe so. Pi over 6 is closer to x-axis, right? Sine doesn't like that, so it's going to be small. It's going to be 1/2. So cosecant is 2. 2 squared is 4. I wasn't saying you were wrong. I was just waiting for anybody else to say anything. And then d theta dt is negative 0.25. Now, why does this make sense? As the sun goes down, what's happening to the shadow? It's growing. So you can see kind of an inverse relationship between the rate of change of the shadow length is negatively related to the rate of change of the angle, which makes sense as the angle. Let me think. How am I going? As the angle is decreasing, then the shadow is increasing.
Yes.
Cool. So we get 1/4 of 4 is incredibly enough 1, so we get dx dt equals 400 feet per second or something.
Per hour.
How did you get that the cosecant of theta is equal to 4 again?
Because pi over 6 is theta.
Okay, so we're giving our okay.
Yeah, yeah. Cool. 400 feet per, sorry, this is per hour, isn't it? Yeah, per hour. Yeah. The shadow. It's almost like it should hurt when it comes through. The shadow, what? Poof. Sorry. Yes.
You do 87. It looks simple, but a lot of things, I think they're constants, looks complicated in a way. Okay, 87. Has like a
yeah.
thing. Oh, just constants?
Yeah.
Okay.
The only variable in number 87 is time.
Okay. So that's not bad then.
A is amplitude, right? C is actually something related to how strong the dampening is.
87.
I don't know if you guys know the other stuff. Right, omega is the frequency, related to the frequency, and the delta is the phase shift. Yeah. Or related to the phase shift, anyway.
What's phase shift?
Don't worry. A pre-calc thing.
Oh.
You don't ask me, let me know that you don't know. Yes?
You got you stuck with phase shift.
See, you're made it. I don't know.
Oh, yeah. This one's freaky. I'll tell you what, let me do this. I'm going to go ahead and give you guys the answer key. 101 is not on the answer key. I just ran out of time. I was doing it right before class. And also there's one that, as I was running where'd it go? The copies, We'll do it together because I made a mistake when I was trying to oversimplify it. So we'll do that one together. Still averaging a decent grade on my practice test.
What's that? Oh, check it. I got you. Thanks, dude.
Bless you. By the way, last Friday was Pie Day, so I have my simplest pie shirt on. But next year it's going to be,
Best pie day.
I was telling my students, they were all looking at me like, I said, next year, man, it's going to be off the hook. And they were like, what? Because next year, of course, is 3/14/15, which is the first. I know. So I'm sure some civilization has something to say about that. The Mayans are like, screw that, and the other people are like, that's where we're all dying.
Today's the day.
Big giant pie comes hurtling towards her. Yeah.
It's going to be 1416 for the NRI beforehand.
Do it again?
For 3.1415, it should be 16 because of the 9 beforehand.
No. What you do is 3.141, so 3/14/15 at 9:20 whatever. You can see how much brain space I've recorded the pi on. I don't know what the next number is. Yeah. So at 9:20 whatever. Yeah. That'll be the time you run out and you start. I don't know what math people are going to do at that point. Yeah, just run around, run up to people and Pyra. What's happening? Yes, please stop me. Just ask a question.
Can we still do 97?
Yes, we can. Somebody was asking me about 97.
Yes, I will.
Because it still looks weird, doesn't it?
Yes.
I got to remember which one I made a mistake with. So none of the natural log ones.
Okay. Probably 5.
Oh, number 36 I got to do over, but 97 is a weird one.
Which one?
97.
Okay.
You could pick up on the fact this is a little weird because it tells you about the volume of a cube and then it asks you questions about the surface area. So you have to be concerned about how those go together. So this is the volume of the cube is increasing at a rate of 10 cubic centimeters per minute. All right, so I think we all know that should be dV/dt. We've done enough volume ones, and you're going to see more of those. How fast is the surface area? So surface area we'll call S of t. So the question: how fast is the surface area when x is 30? Where'd it go? Yeah. And x I'm calling the. Come on, Jeff. X is the length of the side of the cube, right? Okay, so thankfully it's a cube, so there's no other dimension than the one side length that I need. Okay, so there's a lot going on here. So first off, the volume of the cube is x cubed. That's awesome. And the surface area of the cube,
6x squared.
yeah, because one area would be x squared, and of course there's 6 faces. So the surface area is 6x squared. Okay. So I kind of started and did some half-assed thing because I was always trying to tutor people in my office, but it all came together in the end. But you could be a little bit neater about it. So what you know is this. Now, if you start taking derivatives of this, you see how there's a dx dt that's going to come out? And then we have no information about dx dt. And of course we don't know what ds dt is because they're asking me for it. So even if you get this far in the setup, you might be like, I got too much shit I don't know. But you do know this, which is a relationship between v and x. So if you take derivatives, it'll be the relationship between dv dt you know, and dx dt which you need. How are we doing so far? Is that
Great.
So step one, before I can even use this to answer the question they have, and actually if I try to, what do I get when I do this like I said? dx dt equals. So then you see there's a dx dt component. Now I didn't even go this way. If you could look at my answer key, what I did was I made a direct relationship between these two, but it will still work either way you do this. Let's see if we get the same answer I got if we do it this way. Right? You guys, you can look at that or not. So if I attack this, I go, oh shit, I don't know this, I don't know that, this is useless. Right? Yay, this I don't know equals 12 times this other thing I don't know. So what's dv dt from the formula?
It's 3x squared dx dt.
So now I can solve for dx dt. And I still, the whole thing is at a time when x is 30. So I can see what dx dt is at a time when x is 30. And then use that to figure out what ds dt is at a time when x is 30. Yes, sir?
So how do you get the 3x squared?
Just taking the derivative of this, yeah. So if dv dt is 10, x is 30, 30 squared is 900. Dx dt equals...
And divided by 3 times 900.
Yes! So it'll be 1 over 270? Maybe? Yes. Alright. But I mean, I want you to, this is what I noticed after I finished writing this out. Notice, and there's things you can notice that'll make a problem quicker. Unless you spend too much time looking for them if you don't see them. And I've said that before, and I don't know, maybe I made the most sense right then. It still didn't make that much sense. So right here, what is s? 6x squared. So dv dt is actually 1/2 s dx dt. That actually helps, because then I can solve dx dt. Let me show you. Dx dt would be 2 dv dt 2 over s. Is that cool? And then what's really nice is when if I plug that in, well, the way that I did it. Shit. I don't know if I want to do all that way. The way that I did it, screw it. I'm not going to go that way. You guys can see what I did. Well, if you want to on the answer key and see how that might help me out. Let's just keep going with what we got. So we know dx dt is 1 over 270. Not worry about the units at the moment. I can just plug that in here. So ds dt is 12. What's x?
30.
Good. At a time when x is 30. And dx dt we just figured out because we knew what dv dt was. Right? And of course that
4 over 3.
is 9. Good. 4/3. I forgot what all centimeters. Squared. Surface area per minute. Right, minute. And I got 4/3 and I just didn't put the units down, so I have to lose some points there.
So where did you get the 6x squared? I'm sorry, I missed that. For the surface area is equal to 6x squared?
Oh, look at the shape we're dealing with is a cube. So what's the area of one face? X times x. How many faces does it have?
Oh, okay.
Cool. But, you know, if you ever have a problem where you don't think I'm giving enough geometrical information, like you forgot the formula or you don't see what the formula is, just go and ask me. And I'll pretty much do exactly what I just did. You know, you can see it. Yeah. Okay. Look real quick at number 36. Can somebody tell me what I was trying to do and what mistake I made?
It's 36. You got another person. I'm thinking of the angle.
So you could attack it the way it is, or you could simplify it a decent amount. Because, for example, how can you simplify this piece? What does that 4 want to do? Bring it down. The square root of 4 is 2. And then I have the square root of t. And I should square root of natural log of t. But I just forgot to put that 1/2 right there. Which, of course, makes the derivative easier, but it's a bad way to do that.
Wait, shouldn't it be natural log of t to the 4th? Is that what you have?
The 4 comes down.
Ah, right, okay.
Square root of 4 is 2. t to the 1/2, and then the square root of natural log of t, so natural log of t to the 1/2. Can that 1/2 come down? No, it's only when the log of the argument, and the argument has a power. It's not when the log itself is raised to a power. Right? A power can't become multiplication.
Unless you're taking the log down.
So again?
Unless you're taking the log down.
Yes, sure. And then it can come out of that other log. So if you have two logs stacked up, yes. So how should this work then? What rule do I have to use? What's the primary rule? Product rule. So what's the derivative? The nice thing is there.
1.
Good. 1t to the, and then leave this due to 1. Plus 2t to the 1/2, and then what happens here?
1/2 natural log of t to the negative 1/2 times 1 over t, right?
Good. And that was because of the
Chain rule.
chain rule. The inside function is ln t. Derivative of that is 1 over t. Cool. And now you just clean it up. Not too much I could do. They both, yeah. They're both, no, not quite. Let's see what happens here. 1/2 of 2 is gone. T to the 1/2 divided by t is t to the 1/2 divided by t. 2. Yeah, so t to the 1/2 on the bottom. You have a natural log of t to the 1/2 on the bottom. And on the top you have a 1. I think it's the only thing left up there.
Yeah.
And if I really wanted to clean this up, if I multiply this side by natural log of t to the 1/2 on the top and bottom, LCD, but what's this?
That's all squared. Like, on top.
Half a natural log of t times half a natural log of t makes a
Just a natural.
whole natural log of t. Got it. Gruesome. But if you stop there, that'd be fine. You don't have to do all that crap. When I see those half powers, and I kind of see, you want to kind of complete them. You want to complete them. It's just nicer than having square roots and stuff. Yes, sir?
How'd you get the 1 over t to the 1/2?
So, the 2's went away. This went down. T to the 1/2 divided by t is t to the negative 1/2. So I took that down. Yes, sir?
How do you explain what you get from the first step to the second step?
From here to here?
Yeah.
So this is square root of 4t ln t. Is that cool? Does the 4 come down? Square root of 4 is 2. Square root of t is there. Square root of ln t is there.
Yeah.
Okay. Now, did you have to do any of that? You could have just worked with it the way it was. You should get something that would simplify to be that. So it really depends on the way that you look at it to begin with, which is to lead you to where you might stop. So I have to be ready for any of that, right? Okay. So now it's totally up to you guys. So that was the one that's wrong on the answer key. I left out that poor little 1/2. I was overly optimistic. Yes, ma'am.
Can you do 1H?
Yeah, that's gross.
Can I come up and grab the practice test?
No. Yes, come on. I like the look in your face. You're like, really? Sorry. Oh, Jeff. That's evil.
This is a solution, right?
This is the solution, yeah.
Oh, here.
This is a solution.
Yeah.
I don't have the. answer.
Oh, sorry. Here.
Thank you.
There's a hard way to do this, and there's a much easier way to do this.
Curious is the hard way.
And I think on the answer key, I think I did it both ways. I can't remember now. Yeah, I did it both ways.
My 1H is totally different.
I want to do the hard way first, just to show you, because you know I'm going to have somewhere. I'm going to have either like 8 to some weird ass power, so you gotta remember, I mean, if I had a to the x, what is y prime gonna be?
8 to the x times ln 8.
Exactly. What if I had log 8 of x? What would the derivative be?
3y.
1 over
Yeah.
And the reason is, what's the change of base formula say here? It's natural log. What goes on the bottom? The base goes on the bottom.
Makes sense.
The other dude on the top. And this derivative would be 1 over x, and the ln 8's already down there. That's actually where that comes from. You guys see that? So that is a derivative rule you must know. So you know I'm going to put something on there that might be a little bit uglier than log base 8 of x. This one, if you look at it and don't realize what you could do, you have to start attacking it. And the most immediate thing that I need to take derivative of is what? What do I really have here? I have twice the natural log of stuff.
So we have to take the derivative of natural
Good. So it'd be 2
over 1 over x, which is 3 tangent, 3 raised to the tangent of 5x minus times the derivative of x.
and that's where this is going to roll in, right? So what's the derivative of 3 to something?
3 times something times root.
Yeah, 3 to the something.
Times ln 3 times the derivative of the top.
Yeah, good. Times ln 3, because the base is not e. Times
Secant of that stuff.
the tangent 5x minus 3
Yeah.
derivative. Good Lord. So what's really nice here? Just cancel. 2 ln 3. What's the derivative of tangent of stuff?
Secant squared of stuff times
Secant squared stuff times.
stuff prime.
We put it out here. 5. Good. The derivative of the inside. So you end up with 10 times ln 3 times this. The easy way to do this problem, 10, is from the beginning say, I don't like the way that Jeff wrote this. So I'm going to apply legal rules. You can't just say, I don't like that. I'm going to apply legal rules. And of course, the natural log of 3 to a power, the power can come down. And then it's just so silly easy. Because what's the only thing that's not a constant in here? That. Everything else is a constant. So the derivative is going to be twice ln 3 times the derivative of tangent of that. Secant squared
Times the inner.
times 5. Yeah. So it's still 10 natural log of 3. Right? So whenever you have a natural log in there, just take a second and say, can I simplify this somehow? Because if you can, the derivative's got to be the same. Because it's I know that this function is the same as that function. So therefore the derivatives must be the same. Yeah.
I can't remember for I think a quantity to fit multiplied by quantity of something. Can you add the ln to bring down the thing and simplify it to add them? Or does ln have to be there to get that derivative? Because I remember it being easier that way.
Now that we know implicit, if I had something like 8x minus 7 to the 11th times 4x minus 3 to the 14th over 6x plus 2 to the 3rd.
Yeah.
Right? Sure. That would be really disgusting.
Yeah.
But it really, well, there's a simpler way to get a derivative. But what I really want you to realize at the same time, and I got to be careful when I say this, natural logs make the derivative easier to get. But the form it ends up in is not normally the most immediately useful form. So there's a bit of a trade-off. So if I do apply ln, what happens on this side?
You get 11 ln of that stuff plus 14 ln of that stuff minus 3 ln of bottom stuff.
Yeah. And that, of course, is much easier.
Yeah.
Right? One of those is pretty simple. They involve putting it over and then times the chain rule for the inside, right? So this would be This one is, what's the derivative of that?
1 over
One comes over.
I like it.
11 over 8x minus.
Times
8.
88 plus 14 times 4, right? You gotta see it.
Yeah.
You guys see that? Plus 14 times 4 is 56 over 4x minus 3 minus 3 times 6 is 18 over 6x plus 2.
Turns away.
You got to multiply by the y to get y prime of itself, and y is that crap. So it'll be y prime equals that times that, which is the derivative. Sure, it's the derivative, but it's not in a very useful form. So you do trade off that. Depends on what you have to do next.
So it's easier to solve, just
The first time.
It's easier to get the derivative, but the form you end up with is not a very useful form for what you know next, which is to set it equal to 0 normally. That's what you're really interested in. You guys with me?
Yeah.
I would not be as evil to do that to say, find the derivative, and then later say, find where this equals 0, because then you might start working with this, and that's not an easy thing to do. Trust me.
so would you want to do the quotient rule?
So I would just, if I knew I had to do further stuff for this, I would use a quotient rule.
You wouldn't want to bring that.
You could bring that up, but then it just makes it. I would probably bring this up.
You probably would.
Yeah. Make it 6 over 2 to the negative 3 third power. Yeah. Considering I used to do that to everything. I never did the quotient rule ever when I was a student. Yeah.
So nothing like that would be on the test. Nothing like that would be on the test.
Something like that will
Right.
most likely be on the test. But I said I wouldn't make you do some further thing with it. Just since you went this route. Which is what I would like to see, actually, is an understanding of how to use LN to help do a problem. What's the other kind of problem that we use LN on, though, to really help?
Variable.
E, right?
Variable is located
Oh.
both base and in the exponent. We don't have any rule that covers that. But I did show you that we have two rules that kind of overlap, and the answer is actually the overlapping of those two rules, answers. I don't know if you guys remember that. I remember that because it's the first time I ever looked at it that way. And I was like, cool, that's cool.
Was it one of the two mistakes that get the right
Yeah.
answer, or was that something else?
No, I think it was right when you had the two mistakes and then you brought them together.
Yes, it's mistaking that problem to be x to a power, which it really isn't, and then mistaking it to be something to the functional power. But if you just add those two things, you get the actual answer. So it's kind of cool. It's like a combination of the two wrong perspectives.
Can you do one of those again?
Okay. X to the, what do you want?
Cosine.
Cosine? Okay. So if I do ln, I get, so take the derivative.
Negative sine.
Yeah, this is a product rule. So negative sine x, ln x, plus
Cosine over x. Is there anything special with the sine x over x? Or is that just...
say again?
Is the cosine x over x anything special?
I think you're thinking about like sine x over x, the
Oh,
limit.
that's for limits only,
Yeah, so by itself it's nothing very special. I'm sure it's special to somebody. So. Multiply the y, but y is this. So please don't leave your answers y times this. That doesn't make any sense because I know what y is. So it's this. Cool? Or not? Yes, sir.
Y equal 8x minus 7 to the power 11. How did it's multiple, how did it become positive, plus?
Because I took ln's. What's ln of AB? ln of A plus ln of B. Yeah. The division would be minus, so that's why, and the powers come down in front of the ln, so the power came down plus the guy was multiplied by minus the guy was divided by. Yeah. Cool.
would you want us to, if we have it in that form, would you want us to go and put it back in the form above, or no?
Take what you end up with here, and that's what, yeah.
I'm saying if you give us the L and Y and all of that, would you want us to put it in just regular Y?
Oh, I see what you mean. Not here. That's a pre-calc problem. Just getting used to how logs work both ways. Here we're going to apply the damn thing and just go one way that makes sense for the problem. Yeah. Yes, sir.
Could you use that? Oh, that's the one I was-
Oh, okay. Yeah, I guess I did kind of jam it in there a bit. Yeah. All right. The thing to realize about number 87 that they don't really say is that the only variable in there is t. Okay, so one quick thing I want to say. Cosine of something, this something actually cannot have any true units on it. Radians are not true units, and you know that. When you multiply radians r times theta, you end up with just meters or feet. The radians just take a step out of the way. You with me? Radians are very weird units. They're not actually really units. They just kind of step out of the way. I don't know if you guys have noticed that yet or not. So anything inside of a trig function has got to be unitless. So since time is in seconds, this omega, it's not a W actually, it's omega, has to be in per second. And that's why this would be related to a frequency. It's hertz per seconds. How much is that important to calculus? None. It's all physics crap, but just to let you know. Just in case it comes up later, you're like, oh, I think I've heard of that once before. So to take this derivative, what's the rule that's happening here?
It's a product.
Product rule. So derivative of this part?
Itself.
It's A.
Yeah, itself. Yeah, derivative of the inside, negative c, good. Leave this part alone. Plus, and actually I know it's going to be minus, because eventually I'm going to get, so this part stays the same. Derivative cosine is negative sine. And then the inside's derivative, omega.
Wait, so the inside of that question was what was it something t plus?
Yeah, so you can make this just a w t plus d if you want to. It's a delta, like the epsilon delta stuff, remember?
Right. So then, but the w, how did you get to omega? Was that omega to begin with?
Yeah, omega is w, especially when you write like I do.
Okay.
Omega is a lot more curvy like that. Looks
Okay.
however you want to think of it. As you temporarily become.
I see. So
Is that
then your
your
functioning is like omega delta in this case are constant.
Say again? Yes, good. And that's the evil part of this question. They didn't say that. But it's kind of, they're assuming it's known, but it's kind of like, I don't know shit. But yeah, that's the thing. And now, of course, the problem really says find the velocity, which is this, and the acceleration. So how many terms would the acceleration end up having unless there's any like terms? This is going to have two parts because it's a product rule. This is going to have two parts. It's a product rule. And I'll kill the suspense. There will be some like terms. Right? You already see it there. But now that you've seen it once, you should be able to do the second derivative, right? Okay.
It'll be very convoluted, I'm sure.
So notice, if I take this is what I had before, right? So if I take the derivative with the e again, it's going to be another negative c coming down. So it's just c squared. And then this part's going to be the negative sign with the omega, so it's going to be negative, negative is plus. And omega comes out. And this is sine. I don't know if you guys are with me. I've already done the work. I just have to. I already know.
Don't you do the product rule twice there? So I see you have the C squared, but then shouldn't you have added that to the cosine? Oh, I see. Never mind.
Yep. So this is product rule.
Gotcha. Okay.
But I know that the derivative, when I derive the cosine piece, I know what I'm going to get. So I just need to multiply that by the negative c that's there. I don't know if you guys see what I'm saying.
That makes sense.
Somebody sees what I'm saying. One person sees what I'm saying. That's fine, because it's just a shortcut to use the work you've already done, because it's repetitive. I've got the same stupid function there again. I've already taken this derivative. Why would I do a bunch more work? Or do the work. I mean, either way it's going to get you there. Right? Now I can attack this guy with the product rule. You put him down here. So again, it's when I take a derivative of this piece, yeah, the c is going to come down, so it's going to be plus cw. And your like terms. Take a derivative of the sine piece.
Cosine.
Yeah, and the omega is going to pop out again, right? So you get minus omega squared cosine. Yeah, thank you.
Yeah, we've got the omega out.
Mm-hmm. Free.
This is really long.
Yes, it is. But part of what you're supposed to get from pre-calc and from this class is to realize that long is not a problem. It just takes a while to write. So I'm like, all right, it's got some stuff to write. It's like an essay I got to write about something or other. Just write all this crap. So the only parts to really pay attention to are this part. That's the chain rule for that C coming out. And that part's the chain rule for that W coming out. And the rest of the derivatives are very straightforward. Cosine of sine, those are very straightforward derivatives. So it's long because it's got all these constants kind of dragging you down, but who cares? It's long is better than difficult. Almost said that. Anyway. Beavis and butted over there. Long. Hard. Alright. My roots are shallow. Okay, so anything else? I like the people like I don't want to ask anything, but I want to hear more.
How many derivatives do you want us to go? Like on the test, how many will you put down?
I could, you've had problems in the homework that said like G, N, X. So it could be derivatives where you have to do several to see the pattern, right? You've done some of those? Yeah.
Would that be on the test?
Can we do a problem from ending? 39, section 3.5.
Oh, his probably battery's dead. My battery's almost dead. So 39. So if x, y plus e to the y equals e, find the value of y prime at x equals 0. Y double prime, sorry.
What number is this?
This is number 39, sorry. Said it and I didn't write it. Section 3.5. Page 215. First thing you notice is that there's a constant up there, right? Good. So don't let that guy hang around. This derivative is going to be 0. So it's
Y. There's the product rule.
yeah. So it'll be y plus
X.
xy prime or dy dx.
Yeah, you want.
So that's the product rule for that. Is it cool? And actually, you see enough of x, y, you start to memorize this. Maybe. Because that's just what x, y is. But plus. Good?
Equals 0.
0.